Okay, let me start to do this presentation. Hello everyone, today's presentation is about a paper named An Approximate Dynamic Programming Approach to Dynamic Pricing for Network Revenue Management. To begin with, here's the content of the talk with the introduction and the problem formulation, and then I will go through a linear programming-based approximate dynamic programming, and then I will impose some affine approximation and linear independent demand assumption. Then I will do a compact nonlinear formulation on the original problem. Then I will introduce some alternative formulations and pricing policies. Finally, I will give some numerical results and summary of this talk. Let's begin with the introduction and the problem formulation. Assume there is only one seat. Assume you can see in this graph. Assume we are a airline agent that want to sell seats to the customers with different requests, and assume now we have three flights, A to hop to B, and hop to C, and assume there is only one seat left for the airline from A to hop. In the single leg revenue management problem, the products are seats for each leg, that is the A to hop or the flight or the airplane I mentioned before. So if here we have two customers, the customer A wants to goes from Hong Kong to Osaka. Here the wants to go from A to hop, and the price for this flight is $200, and the customer B wants to go from Hong Kong to Osaka, and finally get to Vancouver. And the price for these flights is $800, we're partitioned by the miles, we're partitioned by the miles, partitioned by the distance. We will see that the price for Hong Kong to Osaka in these tickets deserves the price for the Hong Kong to Osaka in this flight equal to $115, and it equals $815 for the Osaka to Vancouver. So in the single leg revenue, we can see for the flight from A to hop from Hong Kong to Osaka, we should choose customer A to get a higher price, as we should choose customer A as it shows a higher price. However, in the network, we can say it's quite different. It seems too odd, since we know that if we choose customer B, we will get at least more there. We will get $800 more than we choose customer A, because the seats from the Osaka to Vancouver also being sold out for one. So which motivates the use for the network revenue management? That is, the seats on each leg are treated as resources, and the products now correspond to the itineraries. So back to our example, in this situation, in the network revenue management problem, we will definitely choose the customer B to get higher revenue in comparing to under this limited resource condition. And then let's start with the problem formulation. Assume here's a firm with M sources and N types of products, and we'll assume there is totally T customers arrive one by one. And for the initial, we will know that we have the initial capacity of resources equal to C, is C, denoted by this factor. And the price given by the firm is denoted by the R1, R1 in N, length N vector. And then the probability of one customer buying one product is buying product J is lambda ij, and we assume the summation for the probability of one customer to buy one product is less or equal to 1. So which means that any customer comes here would at most buy one product inside this from this firm. And if the customer buys the product J, and there will comes with a resource consumption matrix capital A, and with the Aij to denote the unit of resource I consumed by product J, and the Aij equal to 1 if it is consumed, and otherwise it will be 0. And then this procedure repeats as the next customer arrived. And as for the T selling procedure, for the T selling period, that is the T's customer arrived, at that time the capacity of the resource is xt, and the price given by the firm is rt, and the probability for one customer to buy product J is lambda tj, and also we assume that summation of these probabilities is less or equal to 1. And also we have this resource consumption matrix A to denote the unit of resource I consumed by the product J if the customer buys the product J. And also we have to require that the xt, that the capacity of resource xt now must greater or equal to the J's column of matrix A. That means that at least it should ensure they have enough resource to produce one product J under the current capacity of resource. And then and this problem we can formulate it as a dynamic programming, and we have a dynamic formulation, DP formulation. Here the state is the remaining resource capacity xt, where the state space is denoted by the cal xt. If the time equal to 1, that is the initial time, the state space is the state space is a the state space only contains the initial capacity of resource, the C, and if it's not the initial state, if it is not the initial stage, the state can be any integer. The capacity of a resource can be any possible integer value which is less or equal to C, as shown in this equation. And the action here is a price given by is a price that is determined by the firm with the action space RT, which is a product of the RTJ. Here the RTJ is the price at is the RTJ is all the possible price given at time t for the product J, and we also have these and we also have two cases for it. If there is enough resource to produce a product J, the price can be any any non-negative value. And if there is no enough resource to produce the product J, that is X less than AJ, then we will restrict the action space to the singleton R infinite, which is an impossible value that the customer would like to buy. And the DP formulation for this problem is denoted by the VTX. The value to go for under the state is denoted by the VTX. That is the maximization over the summation of the summation across all the products J inside the N. J belongs to N, and with the N is a maximization over the price J. The value to go is to find the optimal price offered by the firm that could maximize the return under the current remaining resource capacity xt. Here the first part is the probability of buying product J under the price R times the reward gained by the sale, and times the reward gain by selling the product J plus the plus the next time plus the time to plus the reward to go under the remaining resource capacity x minus a J for the next state, and plus if the customer doesn't buy the not buying product J times the reward to go at next state under the resource capacity x, and it can be simplified into this form. With simple mathematical computation. And that is all the background we need to know for this paper and for this problem. And then let's start with a linear programming based approximate dynamic programming. That is to considering the whole problem as a linear programming problem, and all the dynamic programming, all the DP formulation are stated into a constraint with every xtx to take the upper bound for the real value, and finally we do minimization to find the closest result and force and push the VTX to push the value to be close to the optimal value. I think it's quite straightforward. And then in general, and this remains hard to compute. So for the in general ADP technique, we consider a value function approximation, that is to assume the VTX equal to the this affine function, and here the theta t is a constant basis functions, and the VTB is a weight for each basis function, and the phi bx is the preselected basis functions, and this is a general form for the ADP. For other ADP papers, for many ADP papers, and then we can submit, and then we can. And we can. General framework. And if we substitute into the problem, we will get this p phi function. And here we can notice that there are infinite constraints in this problem, and it's quite impossible to solve this problem with commercial solvers. So one technique is that if we firstly we compute its dual. Firstly, we find its dual problem, the d phi function here, and we can see, and also since the primal problem has infinite constraints, the dual problem have infinite decision variables, which is very one commonly used technique is a column generation for this infinite decision variable in a programming problem. And so to begin with, before going to the further discussion, let's first discuss or introduce the column generation formulation method. That is to solve these semi-infinite linear programs with an infinite number of decision variables, such as this maximization problem. Here, the decision variable is lambda, and we assume and the lambda has lambda k. Actually, lambda k, where the k has infinite numbers, where the k is inside and where k has infinite possibility. With k to be where k can be infinite numbers, where the k have infinite elements, infinite number of elements. So the decision variable there are infinite number of decision variables. And for example, to help under to help with better understanding, we assume there's a canteen problem. Here now the BK is the selling price for the case dish, and the lambda K is the quantity of case dish we sold, and the AK is the resource consumption of case dish such as the protein or the vegetables, and the C is a total resource budget for each resource is a resource budget. And not all, and we know that not all the decision variables contribute to the optimal solution. Since we can take some variables, we can choose some. Not all the decision variables contribute to the optimal solution in this problem. So we can start with a subset of variables that we choose. We maximize over the summation of the K prime set over the summation of K prime, not a K. And in the canteen problem, we can start with only selling the rice and the chips. And now, after solving this problem, we will know the marginal price of each product. And solving this problem, if we put this problem into any commercial solver, it will return us with the optimal decision variable solution of optimal the solution for the primal decision variable and also the dual decision variable, where the dual decision variable for the first constraint, that is the marginal price of each type of resource under the current menu, that is under only selling rice and the chips. And if we denote the primal the dual variable as x and the optimal solution is x star, then we can try to find the variable that has positive reduced cost by this formulation. Here we can see the BK is the selling price and the AK is the consumption, is the resource consumption, that 2 times the marginal price of the resource. And if we look at if we write out the primal problem explicitly, we can see that this is actually that is actually why we're trying to find a decision variable K here, that we're trying to find the K that violates the constraints as much as possible. And in the canteen problem, that is, we want to find one dish that has high selling price while low marginal resource price, which means that we know this dish can gain a lot while in the and then we add this decision variable to the master problem, that is to the master problem that we changed, and now we changed our K prime set to the cal K prime set to the cal K prime set, and we try again to find the dual variable to solve this problem and find the dual variable, and we get the new marginal price for each types of resource under current menu. And we repeat this procedure until we cannot find no decision variable with positive reduced cost. And then, and at that point, we think we already find the optimal result and optimal decision variables for this semi-infinite linear programming problem. So this is the procedure or the main idea for the column generation method. So let's come back to our problem. So we can do the column generation on the dual problem and then get the optimal value of the primal problem. Here is quite different that here the minimization here for the for the for the problem here we can see that from the we can get the optimal value of the primal problem. Here we, in case we don't remember, in case we already forgot the primal problem, we can see that here is we're trying to find an X and R that allows us to violate these constraints as much as possible. And in the general column generation, we're trying to find a maximization of this problem, and this one is a negative. Some may wonder why we, in our example, in our brief introduction for column generation, we trying to maximize the violation, and now we're trying to minimize the negative of that. We're trying to minimize the constraint that is as possible as we can. The minimization. So this minimization of left hand side minus right hand side is equal to the maximization over the right hand side to maximize the right hand side minus left hand side, so they are equal. And the optimality for the dual problem can be reached when there's no positive reduce cost for all time t. And notice that for general cases, semi-infinite linear programming doesn't guarantee the strong duality. So the optimal value for the dual problem is only an lower bound for the primal problem. However, in this problem, we have the duality gap between the primal and dual pair is zero. That is our problem ensures a strong duality. So once we find the optimality for the two problems, we can already find which is equal to the optimal result for the primal problem. And we can say if we're trying to So here till now, we have already got a brief idea. We already got a general idea for how to solve this linear programming based ADP for the network revenue management problem. And then let's go with the affine approximation and linear independent demand. That is, we impose two restrictions on the general framework. The first one, the affine approximation, that we specify the basis function phi bx to the actual to xi, which is the to xi, and to xi and the linear independent demand. And second is a linear independent demand, means that there's no product substitution, and we denote this lambda tj given rt now equal to the linear independent demand in this formulation. And since we can from the last part, we can see that the price set can be changed because from the under the situation that there are enough resource for producing product J, we change the price at R plus. We change the price for all the possible non-negative value to the range within 0 and alpha tj over beta tj, and we can set the null price R infinite to RTI over beta TI, since once the price is higher than this range, the demand will be 0. So it's meaningless to set the price set larger than this range. And also with these two changes, we substitute into the d phi, we can get the dal with this formulation. And here, the problem has a non-increasing property for the optimal solution phi and this problem also the primal problem. The primal problem has this problem, and it has a non-increasing property for the optimal dual solution theta and v in time t. has a non-increasing property for the optimal dual solution theta and v in time t, which comes from the reference paper. And then we can apply, and this property will help us in the later discussion. And then we can apply the column generation method and notice that there remains infinite number of decision variables as x remains here. So we apply the column generation method with the subproblem CGAL, and now we can see the with the subproblem CGAL, and notice here there has a cross term, there has a square term for the RTJ, the decision variable, makes this subproblem be a nonlinear programming problem now. So this cannot be so under this situation, we need to find a way that to reformulate that we want to help solving this problem. It is nonlinear programming problem now. So how it is nonlinear programming now, so the computational cost might be very high. However, this problem has quite good computational property, quite good structural property, that for the shadowed part, we can denote it as a xtjvx function. Here the minimization over the -1 equal to the maximization over the +1. And if there is any xi less than aij, means that there's no possible to produce the product j, the htj function will equal to 0 because we cannot offer to produce it. And otherwise, the optimal solution of this htj function can be computed with the optimal solution r star tj, denoted in this way. And we can see the RTJ and its RTJ now is irrelevant to the and we can see that the optimal solution and its corresponding value optimal value is irrelevant to the x. So we can define a new function. We can define an htjv function that is the solution. For the optimal value for the capital H function when there's that. We can define an htjv function that equals to the optimal value for capital htj function when there's enough resource to produce product j. And then we can introduce a variable wj to indicate that whether the x is greater or equal to aj or not, and it has to satisfy that the aijwj must less or equal to xi for any I and j. So under this situation, we will have this connection between the capital H function and the H function. And we recall the non-increasing property and the objective for the subproblem. We can see that this shadowed part is greater or equal to 0. So in this case, if we want to do minimization, we wish the x to be as small as possible. However, it has a constraint it has a constraint here, so we can shrink the value of xi to be I if the aij wj equal to 1. Otherwise, we can let the xi to equal to 0. So the subproblem now can be reformulated to a bilinear integer programming with this simplified objective function and this constraint for the combining the x and w, and finally the binary constraint for these two decision variables. And this could quite, and solving this problem is much, and for the with this binary integer programming, if we can solve this, it is much easier to solve than the original CGAL subproblem. So here's the column generation and its simplification for the affine and affine approximation and linear independent demand assumptions. Let's have a quick summary in case we have forgot the previous part. We start with a network revenue management problem with this DP formulation, and we transfer it with a linear programming based ADP P5 problem in this form. And its dual form is D phi, and we have its dual form D phi. And we can say from this D phi, we can do column generation with the pi t subproblem. And this is the first, and we can solve it by the column generation with subproblem pi t. And also, we introduce the affine approximation and the linear independent demand assumption to get a DAL formulation, to get the DAL. And for the DAL, we firstly have the column generation CGAL that could already solve it, but it is nonlinear, so quite difficult. Then we add the WJ into this problem to get the CG1AL that could be used in the column generation with much faster solving with much faster computation. And then, so till now, for much faster computation, and now we want to do something, and then we want to do some reformulation to avoid using try not to using the column generation. Instead, we're trying to establish a compact nonlinear formulation for this problem. And we also, that is, we want to find some compact formulation that could be nonlinear but can avoid using the column generation method. We also start from the CG1AL, the subproblem for the column generation, and we can rewrite the P5 at this formulation. As we mentioned before, the subproblem for the column generation is quite closely related to the constraint in the primal problem, and we denote it as a PAR. Here we can see there's an explicit constraint in we have some explicit constraint here that is quite difficult for us to input this problem into the commercial solver. So to reduce this constraint, we firstly define an indicator function wjx that indicate that if the x is greater or equal to aj, we denote it where the value is 1, and otherwise it will equal to 0. And then we introduce a new decision variable rho tj, that is maximization over this form and 0. And the the left hand side part inside this maximization, inside this max operator, is actually comes from the value for the value for the hv function. If the that actually comes from the value of the h function, actually comes from the value of the h function. So the original PAR can be rewrite as the so by adding these two with these two newly introduced notation, we can write a new problem formulation P1AR in this form. And here we can say it is now a QC convex QCQP problem, but it remains infinite constraint as shown here. So one straightforward and if we to solve this infinite constraint problem, firstly we're trying to compute its dual formula. We want to have its dual formulation with the Lagrangian multiplier mu and delta for these two constraints respectively. And we have the dual problem DAR in this form. Here these forms are in this form, and here the only here we just skip some details. Here the dual problem have a new introduced notation QT mu here that denote that the QT mu is a set that the summation over the x inside the cal xt set. The summation here we the only to skip some details, we introduced skipped all the details here. The only unknown part here is the QT mu set, denote the mu tx wjx, the summation of mu tx wjx over x that is not equal to 0. And notice that even this problem here we also although the primal problem has infinite constraints, the strong duality also holds for the P1AR to DAR, these two. And observing the first two constraints, we can conclude that the mu tx, the summation of mu tx over x equal to 1 for every time. And also we introduce a new decision variable s, and we to solve this fractional presentation of two decision variable mu and delta and mu, we can rewrite the DAR into the D1AR in this form. Here we can say there's no fractional operation among two decision variables, although there remains the cross term for two decision. Although there remain cross term over two decision variable, but this one has already solvable. But we want to there are cross term over two decision variable, but this one can already be solved through the commercial solver. To better help the computational efficiency, we do variable aggregation. Here we introduce a y ti, that is summation of mu tx and xi, and the ztj, that is summation over mu tx and wx, which will equal to mu tx, since there's only if we put the indicator into the under the summation. And we do this two variable aggregation, where we'll aggregate the aggregated form the aggregation will form the D2AR form, and we have the proposition 2 to denote that the A1AR and the D2AR are equivalent. So once we solve the D2AR problem, I notice that the mu here remains infinite number of decision variables. And we know that the A1AR, D1AR, and the D2AR are equivalent, but all the decision variable here are finite and linear to the decision, and all the decision variable here are linear to the time and the product number. So this one is much easier to solve. And even we can do we can find its dual problem P2AR. Both them are tractable SOCP that could already be put into the commercial solver and solve them with quite fast. So here's the so till now we have already introduced all the accelerating method for the original problem. And let's go with the quick summary. We start in this section. We start with a linear programming based ADP P5 here, and starting from the CG1AL, we find we write the compact nonlinear programming PAR with this form. But here the decision variable, the constraints has all the constraint. There are constraints inside the constraint that avoid us to put the PAR into the commercial solver. So we introduce the WJX and the rho TJ to get a convex QZQP with infinite constraint P1AR. And we do dualization and introduce a decision variable S. We get a SOCP with many decision variables D1 AR here. It remains with still many decision variables here. And then we do variable aggregation. We get the SOCP D2 AR. And also we do dualize to get the SOCP P2AR. Both the P2AR and D2AR are solvable through any commercial solver that could, at least they can solve the SOCP problem. And then we have some alternative formulations and in this part, I will go through two alternative formulations and introduce the pricing policies for this problem, for this model. The first one is a deterministic nonlinear program formulation. If we want to establish a baseline, we like to consider a deterministic demand for this problem. That is, we know that the demand, so the optimal price can be computed by the inverse demand function. Here, the inverse demand function are here. The lambda Tj is known and deterministic. And so the problem now can be formulated as how can we try to maximize the demand for each client that they will try to buy our product. We denote this formulation as DEP with the optimal value ZD. And this formulation will be presented in the numerical result. Will be compared in the numerical result. And another way is to do the discretization. That is a discretization strategy. That for each product J, we do not consider a continuous price set. Instead, we consider a price set with K points in period D. That is denoted as the RTJ0 to RTJK-1. And with the corresponding arrival rates, actually the demand rate lambda Tj0 to lambda Tjk-1. And we use a mu Tjk belongs to 0 or 1 to denote whether the price RTJK is offered or not. So the DP formulation is denoted as V hat Tx is a maximization that is trying to find the optimal price offering strategy U that maximize the reward gain for this that maximize the reward gain by this offering strategy. And the ADP formulation following the linear base, the ADP formulation is the ZAD, and in this form. And since the price, and this can be solved by the column generation method, and this can be solved by the column generation method, and this one will also be considered in the later. And finally, we will come to the pricing policy. That how can we determine which price we should offer to the customer, or recall the airline example, the agent needs to determine the prices offered to the customers based on the current capacity of each airline. So assume, take an example, consider an example now. For the scenario 1, we totally have 100 seats for the A2 hop leg. And the price for the A2 hop is $200, and the demand now is 15. And the price for A2 hop to B is 800, and the demand is 16 now. So as a clever agent, you know that we will satisfy all the A2 hop to B requests first, and satisfy the A2 hop later. And we know that they are totally 100, and 100 minus 16 is 14. So we know that we will reject 10 demand for the A2 hop demand, right? So since all the A2 hop to B demand is already satisfied, if there's an additional seat, this seat will only be sold to an A2 hop passenger, as we know there are still 10 unsatisfied demand. So the buy price will equal to 200. So the price as the agent is the buy price will equal to 200. And for another scenario, for the scenario 2, suppose everything remain unchanged except the demand for the A2 hop to B increased to 110. So the clever agent will sell all the seats to the A2 hop to B. However, there are remaining 10 demands unsatisfied, right? And the demand for A2 hop are all being rejected. So now, since A2 hop to B demand has not been fully satisfied yet, and additional seats will be sold to an A2 hop to B passenger instead of A2 hop passenger for the higher reward, higher revenue could gain from A2 hop to B than A2 hop, right? So the buy price is 800. So from these two scenarios, we can see that the buy price is the lowest acceptable price that reflecting the marginal opportunity cost. 把这个放前面。
bouteille. Pantalon.
Occupé. Sport.
Pourquoi tu vas dans ces magasins?
Pourquoi tu vas dans ces magasins?
Haut. La. Foot.
Avec qui?
Vieux.
Bonne nuit.
Tu as peut-être faim?
Tu as peut-être faim. Faim. Faim.
Maman.
À la télé. Bof.
Vent. Bien. Décor.
Elle. Va. Piscine. À. La. Pause.
Il va à la piscine, va à la piscine pendant la pause.
Aujourd'hui.
Un peu.
Sommeil. À plus tard.
À plus tard.
À. Bleu. Déjà. Elle. À la piscine. Pendant. Pause.
And in our DP formulation, we can see this part reflects the marginal price or the marginal price for this part reflects the buy price. And if the RTJ, the price, the given price equal to this, we can say that if the price is higher than this part, we can gain more from the selling, and if the price offering from the agent is less than this part, we will lose our reward. We will lose our gain. So there, and then we will have for the dynamic pricing, we will introduce 4 pricing policies in this paper. The first one is the static buy price. That is, we approximate the buy price with the summation of Aij omega I star, where the omega is the buy price, the marginal price computed by the, that is a dual optimal solution, the optimal dual solution for the deterministic formulation. As I mentioned already. And the second strategy is a dynamic buy strategy. That's where And second pricing policy is called a dynamic buy price. We approximate the buy price with the summation of aij and v star t plus 1I. Here, the v star is the optimal solution coming from the optimal solution from the section we mentioned, the coming from the optimal solution theta and v, and we can take the PAR as an example. And why we use this v to represent the buy price, we can see from this formulation why we use this v, capital V, to denote the buy price. We can see from this affine approximation formulation, if we take the we know that because the buy price is we know that the buy price is marginal price for the is a marginal price for the resource, and if we take derivative if we take derivative of x over the left hand side and right hand side, we can say that the left hand side denotes the buy price, and the right hand side remains is a VTI for each product I. So by definition, that is the buy price for each resource. So we use the optimal solution Vt plus 1I to denote the result. And another type is called dynamic buy price computation, which is quite difficult. Firstly, for the first step, we consider the approximation of the value function Vtx with the value computed by the for example PAR, approximated by the value of VTI, and plus the summation of all k not equal to I with the VTK star plus xk. That is, we consider the buy price is given and static under the optimal solution V star at current, and we're trying to approximate, and the first step is to do this kind of approximation, to avoid any dynamics of the products not equal to I when we only consider the product I, the resource I. And then for the step 2, we solve this minimization problem, which is the result that we substitute the approximation into the original problem P5. And solve this problem, we will finally get the buy price with this approximation. Here the VTI hat is the optimal solution for this minimization problem. And for this computation, we actually want to separate all the dynamics and uncertain from other from other resource, and we constrain our attention into only one kind of resource I, and trying to find the optimal buy price and to approximate the result. And to better denote it, we write it as we write with this formulation. And for the last pricing policy, we named it as static buy price accommodation. The only difference is that for the first step approximation, we change the V star here to the omega K star here, and the omega is the same from the notation here. And finally, we come to our numerical result and our summary. For the numerical, we also consider the hub and spoke network problem. We can see, for example, the airline problem is one hub and spoke network problem. And we only consider two kinds of network. First one is a one hub network. You can see from this left-hand side graph. There is only one hub, and there are S non-hub location, so the resource will be 2S. The number of resources will be 2S, and the products will be S squared plus 2S itineraries. And for the two hub network, these two are hubs, and there are S non-hub locations, and resource are 2S plus 2 flights, and we have S squared plus 4S plus 3 itineraries in this network. And for the first result is a runtime comparison among the continuous formulations. Here we can see the first two column is a column generation result with different accuracy, because if we solve the column generation to the exact results, could be very difficult and could be computationally expensive. So we only consider to stop and some accuracy. Here we can see and stop at some accuracy. And the third and fourth column is a running time for the two compact SOCP formulation. And we can see the reduced formulation, this orange part, is more computational efficiency than the column generation approach. And for the continuous formulation versus the discretized formulation, we see that all the orange part, all the dash part is faced the out of memory error, and we can see there's a trade-off between the solution accuracy and the solution time, because if we treat the P2AR as the optimal solution, we can see the result for K equal to 5 is far away from the optimal solution, and for the K equal to 20, they are quite similar now, but the time already be quite large. And for the K equal to 10, the result is also quite close, but the time uses much less than the continuous case. And then we do comparison among different pricing policies. Here, the BDB as a short for the dynamic by the price decomposition. The bond for the DBD bond is the minimization is a minimization over all the resource type I with approximation, and the SBD bond is a minimization of all the resource approximation under the static by pricing decomposition. And we can say that for this bond, the discretized value is much higher than the value for the discretized policy. A discretized strategy is higher than the affine approximation and higher than the static SBD bond and higher than the DBD bond, which means that the DBD pricing policy is the tight displays has a tighter bond than any other formula approximation method. And regarding the policy performance, we can see that the DBD is greater than the SBD and greater than the DB and greater than the SB. And also, comparing the continuous price and the discretized case, we can see that the continuous formulation provides better policies comparing to the discrete formulation at most cases. And finally, here's a summary.